All right. Let's start off. Let me see. Okay. Hopefully you guys had a chance to submit your assignment, the practice assignment, so that you're comfortable with the process for tomorrow. I think some students yesterday were saying that they had trouble submitting their Word document, or Teams assignment would complain that it wouldn't take that Word document that they're trying to submit. So I don't know if this is the solution, but we could try this. If you're having trouble submitting, maybe it's because you're submitting under the same name as the one that you downloaded. So the one you download from me, you can download that, but when you're ready to submit something else, if you're ready to submit your work on top of that, or let's say you wrote directly on that Word document, change the name slightly, use a different name, and see if that will allow for Teams to take it in, or for you to submit it without any issue. So I haven't gotten confirmation that will fix it, but if you are able to try it, and if that's the issue you're getting, let me know if that works. Other students have said that that if they were to print it out, they will print it out, they'll work on it, and then they will take a photo with their Surface, and that way it's directly on their Surface, and they don't have to go through the process of using their phone. And if they want to submit it directly from their Surface, they can pull that file and put it into a Word document easier. So that's another option. Or students are completely doing everything on their phone because they have their Word document app, they have their Teams app, and they're able to do that transfer seamlessly. If you have your file in JPEG or PDF, that's fine, but as long as you can somehow get it into a Word document, that will be the best case scenario for me in terms of being able to access it and grading it, and makes things a little more efficient for me. I think some students were asking whether they can submit it as a link, and I think that works too. Some people were able to share the link with me, and I was able to pull that up as well. So yeah, I think sharing a link is acceptable as well. Any questions or any issues that you guys are running into, or have you guys been able to try it and successfully submit it as a Word document? Okay. If you experience any issue later today, or if you have any questions, feel free to reach out to me through Remind, either about the submission process or about a question that you have about the test. Okay. This is on the test review 1. We did number 2, which we talked about how with continuity conditions, when you see greater than and less than, that's an indication you have to think of 2 separate one-sided limits, because you have differently defined expressions on either side of 3, and we need to gather information from both sides separately. And because these didn't agree, we can stop and say second condition fails, limit doesn't exist. We have non-removable discontinuity. Let's try number 3. Again, we're going to step through continuity conditions. In this case, we're going to, if we just step through it, we'll be able to figure out what K is. Okay, so it would just be a process that as long as you go through continuity conditions, you're good. But there's something a little different about our restrictions here that I want to talk about. But first things first, we want to find the ordered pair. What's our C value?
-3.
Yeah, always given to us, right? You don't have to guess. It'll always be explicitly stated for you. And what's f of -3 equal to?
K.
Yeah, that's all we know, right? We just know it's K. Okay. We'll come back to it later, but right now we just leave it as it is. Move on to our second statement. We want to find the limits. Now, this is just an ordered pair, right? This is just a point. Your connected parts of graph is actually all contained within this expression. So unlike the previous statement where we have differently defined functions on either side of of 3, here we have the same function defined on either side of -3 because it exists everywhere. This is our defined expression on the left side of -3, on the right side of -3. It's just at -3 we have something else defining that point. So when you see this notation, there's no need for one-sided limit because the left side, the right side is all defined by the same expression. So when you see this notation, all you need is one limit statement. When you see this notation, you need 2 one-sided limit. Okay. Do we all see the distinction there? Okay, everybody good so far? So now this is just a limit problem algebraically. So what would you do first here?
Plug in -3.
Right, plug in -3. Let's not assume anything, right? Let's not assume whether it's a real number or a whole or a vertical asymptote. Let's gather that information. Let's convince ourselves what's happening before we assume and take steps that we think we need to take. Always plug in that whole number first. Okay, so -3 plugs in. Okay, we get 0 over 0, so now what can we conclude? What's happening here? Now we know there's a what?
Vertical asymptote.
Not quite.
Is it
There's a hole. There's a hole. Okay. Yep. So when you see 0 over 0, I want you to think there's a hole. If you see 10 over 0, then that's when you know it's a vertical asymptote. Okay. And if you see 0 over 4 or 0 over none, that's just 0. That's a real number. Okay, let's make sure that we're clear with all the distinctions of zeros. Okay. Good. All right, there's a hole here. And if there's a hole, we know that the limit exists. It's just kind of hidden from us. Okay, we know the limit exists. We just have to do a little bit of cleanup work. So what cleanup step can we do?
Factor the top.
Yeah, factor the top, right? We're trying to get the x plus 3 to show up somewhere up top. Yeah, anytime you want to know where that factor is for the whole, just look in the denominator. Okay, you know, okay, whatever's in your denominator, you're trying to get that to appear in the numerator. That's what your goal is. Okay. Multiplies to be -6, adds up to be 1. We find the common factor, goes away. Now we reevaluate, right? Now we should be able to get a real number out of this because we've been able to remove the obstacle. So -3 in for x. So we find our limit. Our limit exists at -5. Keep going, right? What's our third condition?
One and two have to be equal to each other.
Have to be equal, right? So f of -3 has to equal to the limit as x approaches -3 of f of x. Well, if we look at our result, we're forced to have to set k equal to -5, and there we have our k value. So if you follow the continuity script, everything will work out in terms of what you're looking for. You don't have to do anything outside of your condition.
I have no idea what just happened on that third step.
Okay, that third step. So here is our continuity condition. Where's my sheet? So here's what the conditions say. Condition says the point has to be defined, right? The limit has to exist. And then finally, the point has to live where the limit is, if we want to guarantee continuity. So let me draw a picture of what's happening here. It says f of -3 is k. Okay, I don't know where k is, so I'm going to leave that alone. The limit as x approaches -3 is -5. So maybe something like this. We know the graph is going to connect, but there's going to be a hole there. Because, right, we discovered there was a hole, but we know the graph is connecting to -5.
Okay.
So where does the point have to be if I want this to be continuous?
Wouldn't have to be 3, 5. Well, -3, -5.
There it is. Yeah, so that's how we know our K must be -5, because that is where our hole needs to be filled in.
Okay, thank you so much.
Yeah. Let's jump to worksheet 2. And I want us to practice again through these types of piecewise function. I think this is a good way for us to see the mixture of different limit problems and be able to distinguish between infinity with real number, with one-sided limits, with holes, with asymptotes. Okay, so I think having a mixture of them is going to hopefully help us clarify in our heads the subtle differences in terms of the approach for each type, if we can understand what steps we take for each type of problem. I just want to kind of make sure we have a visual on this. I don't expect you to graph it or anything like that, but I just want us to kind of have an idea like where these are located and what these, in terms of the relationship to each other. I want us to visualize these are 3 separate segments. You got a segment to the left of 2, you got a segment between 2 and 5, you got another segment to the right of 5, but these ones are just random ordered pairs that's sitting at these points. So again, this is not an accurate graph. I just want you to be able to have an idea where these are located on the graph. So we got some branch that is to the left of 2, whatever that looks like. You got order pair at 212. I'll put that somewhere up here. We got some segment that connects from 2 to 5 with this 2x minus 5. We got some random order pair that's sitting at 520. And then we have another stretch of the graph that's going to extend from 5 all the way to infinity. Right. Not accurate, but I just want us to understand these as 3 segments with 2 random order pairs. Okay, first up, limit as x approaches negative infinity. So negative infinity means that I'm going to be starting on the left edge of the graph, and I'm going to be heading off the grid to the left. So I'm moving in this direction. And if I'm moving in this direction, I am clearly sitting on this piecewise, because I'm dealing with graph that is less than 2. I'm headed towards negative infinity. So I'm looking at the first piecewise for part A. All right. What procedure do we follow if we're approaching negative infinity? Right. We don't plug in, right? That's not the first thing we do.
Compare degrees.
Compare degrees, right? So I find my highest degree, which is degree 1 up top. I find my highest degree below, which is also degree 1. Matching degrees means that there is a horizontal asymptote And the way we find that horizontal asymptote, we pick the coefficient. We look at the numbers in front of those variable, and whatever that fraction is, that's going to be our limit, our horizontal asymptote. So as we exit the graph to the left, the graph is leveling off at a y value of 1/2. Okay, next up, we're approaching 2 from the left side of 2. That means I'm starting slightly to the left of 2, but then I'm moving towards 2. So I'm still sitting on this segment here, right? This connected piece of graph. Less than 2, slightly less than 2, up to 2, that's going to be this one here. Okay. First things first, what would you do here?
Plug in 2.
Just the 2, right? Just the whole number. We're not going to look at that one-side limit yet, or we may not need to at all. So 2 first, and because right now we just want to gather information, right? When we plug 2 in, we'll be able to know exactly what's happening there, and then we can decide what our next step is. So plug 2 in for x. And what do we get?
7/0, so the limit does not exist.
Because visually, what's happening here? There's a what there?
Vertical asymptote.
Okay, there's a vertical asymptote. You're right, the full limit doesn't exist. But this is not asking for the full limit, right? It's only asking for the approach from the left side towards that vertical asymptote. So to visualize our options here, maybe the graph looks like this. Maybe it's going up, right? But then there's another option, right? Maybe the graph is doing this. And so the question is, how can we tell between these two options if we don't have the graph in front of us?
Plug in 100.
Okay, not 100.
Negative 100.
Not that either. I'm glad you said that because that is a common misconception, and I'm gonna we'll circle back to that. Something else.
0.9.
1.9.
Yeah, we wanna choose a number close to 2. Okay, so from the left side of 2, so we're gonna choose 1.9. Okay, we're choosing 1.9. Okay, let me finish this first, and then I want to address the question about why is it not 100 and negative 100? Okay, we'll talk about that. So 1.9, because we want to find out, you know, close to our target, right? We want something that's close to our target to test against. So 1.9 plugs in for x. Numerator, we get positive. Denominator, 2 times 1.9 is slightly less than 4, right? Or sorry, 2 is less than 1.9 is less than 2, so this is slightly less than 4. It's like 3.8 minus 4 is going to be negative. So we know that this is going to be negative infinity. That means our graph is going to be more like this. Now the question or the comment that someone asked or suggested, Why, what about 100, right? When do we test 100? When do we test negative 100? We only test 100 or negative 100 if we're actually moving off the grid towards infinity. Okay, so let me show you when we do that. We do that if the problem looks like this. If we're approaching infinity, and then if we realize that our degree up in the numerator is higher than the degree in the denominator, then we know that there is no limit. We're either choosing between positive or negative infinity. And now, if you're choosing between these two options, but you're headed towards infinity, which is completely off the grid, which is a large number to the right. So here we can test 100. And when we plug 100 in, we can confirm whether it's positive or negative, and then we can decide this. So let me put these next to each other. Do you guys see the distinction here? We want to plug a number. Once we decide there's a vertical asymptote, we want to choose a number close to our target. Right? If we choose 100, 100 is not going to give us information about, that's too far away, right? There's too many things that are happening away from it. That's not going to give us a good read as to what's happening at 2. But if we're headed off the grid and we realize that our degrees are higher than numerator, then you're going to be testing either 100 or negative 100, depending on whether you're moving off the grid to the right or moving off the grid to the left, which is negative 100.
Okay, thank you.
All right, good. So student from previous period also asked about this. So I think, right, we want to make sure we know what numbers to test depending on which situation we're in. Okay. Okay, limit as x approaches 2 from the right side of 2. So now we're starting slightly to the right side of 2. We're moving towards 2. And that is going to be this middle segment, 2x minus 5. Because 2 is between, slightly to the right of 2 is going to be in this interval, right? First things first, whole number. 2 times 2 is 4. 4 minus 5 is negative 1. We get a real number, so we stop. Nothing more to do, right? This one-side limit only gets activated if we're trying to decide between these two options headed towards vertical asymptote. Any other situation, it's just kind of a distractor. It doesn't have any impact on our steps. Okay, so how would you approach this problem? Limit as x approaches 2. What would you look at to determine the limit as x approaches 2? Or what would need to happen if the limit as x approaches 2 is to exist?
The B and C would have to be the same answer.
Right. You see how there is a split in different graphs on either side of 2? So we have to rely on one side of limit so that we can figure out, are these two separate graphs, are they moving towards the same y value from both sides? And B and C allows us to gather that information, right? B and C is kind of setting us up for part D, because we gathered information that from the left side of 2, it's going to negative infinity. Okay, so this is not an accurate graph here. Right, maybe something more like this. As we approach 2 from the left side of 2, the graph is going to negative infinity. But then as we approach 2 from the right side of 2, it's going to -1. So obviously, these two are not headed towards the same y value, not headed towards the same real number y value. So there's no agreement from both sides. Limit does not exist. Okay. Approaching 5 from the left side of 5. So that means I'm starting slightly to the left of 5. I'm headed towards 5. And that's going to be in this region here, right? Less than 5 headed towards 5. So also 2x minus 5. Plug 5 in for x. We get 2 times 5 is 10. 10 minus 5 is 5. Approach, okay, any questions here? Approaching 5 from the right side of 5, that means I'm starting at a point to the right side of 5, headed towards 5, and that is clearly on this last segment here. Okay, first things first, right? Whole number gets plugged in. Let's gather some information about the behavior of the graph at that point. 5 goes in for both the x's here. So this makes it negative 25 plus 4, which is negative 21. And that is going to be a clear indication that we're dealing with a vertical asymptote. So we look back at our problem, we realize we're just moving towards the asymptote from the right side, which means that we are dealing with two options, right? We're either dealing with the limit doesn't exist, there's a vertical asymptote. We're either dealing with positive infinity or negative infinity. So we want to choose a number that is close to 5, but moving towards 5 from the correct side of 5. So I'll choose 5.1. So 5.1, I can plug that in for my expression here. So I get negative 25-ish plus 4, which is negative. 5 minus 5.1 is also negative. So negative over negative is positive. So I know that from the right side of 5, my graph is going to be shooting up to positive infinity. So my graph is going to look something like this. Okay, any questions so far? Part G, limit as x approaches 5. So do we have some previous information we can use to conclude what our limit is?
E and F.
Yeah. Approach from the left is not in agreement with the approach from the right. These are not headed towards the same destination. Limit doesn't exist.
So is that problem basically just like the third condition?
Let's see. Can you expand on that? What do you mean?
So like for those like the set of conditions, like those rules, like the first, second, third.
Yeah,
You
yeah.
do like the one side and then you set them equal to each other. Is that kind of like what we're doing with that problem?
Kind of, right? But this is actually part of the second condition, right? So basically what we did was we found these two results. We found that these did not agree. So we concluded that the full limit doesn't exist. Because B and C provided this information and we see that these are not in agreement. So our overall conclusion is that the limit doesn't exist.
All right, that makes sense.
Okay. Okay, approaching 3 from the right. 3 is squarely inside this interval. So we just look at the 2x minus 5. Okay, 3 in for x. Approaching infinity here. So now we want to follow the graph off the grid. So that infinity is talking about values greater than 5. So it has to be with this last one here. I'll put this down here. All right, what do we do when we see infinity?
We compare the degrees.
Yeah, compare the degrees, right? Numerator is higher than denominator. So that's going to fall under this third option, which is we know our graph is either headed up or going down as it exits the graph, as it exits from our view. So we know based off of our degree comparison, it's either going up to positive infinity or negative infinity. So now, because we're choosing how the graph is headed off the grid and we're headed towards infinity, now we can test 100 because 100 is in the direction that we're headed towards. This is how we're going to decide between these because, right? But if we're headed towards a number and we want to get something close to that number, then we have to use decimals. But here, right? We want large numbers, so 100. Negative over a negative, which is positive, so we know we're dealing with this option here, positive infinity. All right, I want to talk about sketching a graph here, so let's look at number 9. I want to focus first on this A and G here. I want to help us verbalize and visualize how to interpret it and also how to graph it. So whenever you have limit as x approaches either positive or negative infinity, I want you to think of this as you're following the arrows moving off the grid of our graph. So a lot of times it's going to be end behavior, and then sometimes it may be horizontal asymptote. Basically, how are the arrows pointing as we exit the graph? So let's look at A here. Here, we're approaching negative infinity. So that means we're going to start at the left edge of the graph, and we're moving off the grid to the left. We're moving towards negative infinity. And this is telling us that as the arrow is exiting, it's going to flatten out at a y value of 8. So when you see this notation, you know that you're dealing with some horizontal asymptote. All right, so let me show you what that could look like. So we're going to exit the graph to the left. We want it to level off at 8. So I'm just going to sketch a graph here where I'm leveling off at 8. Okay, so you can have this, or if you want to come from a higher value, you can have it over here as well. So it doesn't matter, as long as however way you draw it, you have your graph flattening out at 8. That's what we want. Here, we're also exiting the graph, but now we're starting at the right edge of the graph, and we're exiting to the right. And as we exit to the right, we want the arrow to level off at -4. So maybe you want to draw it this way, or you want to draw it this way, however way you want to do it. F of -5 is equal to 3. That's just an ordered pair. The limit as x approaches -5 does not exist. So you have a couple options here. So if the limit doesn't exist, you can either make it a vertical asymptote, you can make it disconnected segments, or you can make it an endpoint. So if I want, I could make an asymptote on both sides of -5, or I'm just going to do disconnected segments, but you have options available to you here. So this disconnect the segments just means I have something like this. Eventually, I'm going to have something where the graph is not moving towards the same y value. Or if you want to have it where you have asymptotes on either side and that point is just sitting there, you can do that as well. Okay, so study for your tests. If you have any questions, send me a message through Remind or email. I'm going to have a morning review session at 7 o'clock. So I'm going to finish this problem just for the recording. If you want to stick around, you can. But feel free to go, but you know, I just want us to finish this problem in case students want to access it for later. Okay, so if you have to go, have a great day, and I will see you tomorrow. Okay.
Mr. Yang, is that hole supposed to be on -5 or -4? The bottom one?
Oh, sorry, you're right. Yeah, it should be at -5.
Okay.
I'm not directly over my paper, so my
You're
view is a
good.
little off. Thank you.
You're good. I was just wondering.
Okay, so if you have to go, feel free to go. I'm going to finish this problem, though. You can stick around if you like. So, order pair, we're good. Limit doesn't exist. Okay, you can do your own interpretation. Everybody is going to have something a little bit different, which is fine. Limit as x approaches 1 from the left is equal to 3. So, I'm going to have a graph at order pair 1, 3. And I'm just going to connect to that point from the left side. Approaching 1 from the right side of 1 is -4. And then finally, the limit as x approaches 3 is positive infinity. So when you see infinity, this is talking about the behavior from both sides of 3. Okay, we should have a mirror image on both sides of 3, both branches going up to positive infinity. So I'm going to create a dotted line at 3. So this is okay. If you want to leave your graph like this, you can do it. I'm just going to connect just to make it a little bit nicer. But as long as I don't see any issues with failing the vertical line test, you can leave your graph like this. So I do want to point out something about arrows. When you're looking back at your graph and you're looking at your arrows, you should only have arrows exiting the graph or moving up and down along a vertical asymptote. Okay, you know, okay, so here's a red flag. If your graph looks something like this, where you have arrows pointing, if you're on opposite ends and then you're headed, you're pointing towards the graph, that's a problem. Okay, because I'm going to follow the arrow and I'm going to say, okay, eventually they're going to overlap and it's not going to pass vertical line test. Okay, so we don't want to do this. So the only time you should have, the only arrows you should see on your graph that are safe, exiting the graph or going up and down asymptotes. Okay, have a great day, guys. See you guys tomorrow, but feel free to reach out if you have any questions over Remind.
Thank you, Mr. Yang.
Thank you.